Yes, only. Okay.
Okay.
Yeah, it's okay. It's recording now.
Okay. Okay, so today, I don't know, there are few people and Fatma Noor Bajwa is here. Do you know the reason why less people are here? Fatma? Okay, give me just 1 minute. Okay, so I hope there will not be a misunderstanding because of the timing. And okay, Mauritius is here now. You are late, Mauritius, today.
Sorry, I have to breakfast.
Okay, okay. Breakfast. So, David, you finish your breakfast?
Uh,
No, no.
uh,
Yes.
Okay, so we start now lecture 9. Lecture 9 actually is very important. In this lecture, what we are going to do, we started the Q switching technique, the laser, and what is Q switching technique is basically to have a giant pulse, not the short pulse, but giant. So you can have like a huge energy or something like this for a certain application. And so, as I mentioned, that the Q switching is a starting point. I mean, when you start learning about the pulse lasers, there are different Q switching techniques, and some of the techniques are slower, some of the techniques are faster. It depends. I mean, uh, how longer pulse, how long pulse you need, and what kind of applications. So here, if we start now, let's move to the first slide here. This was actually, if you remember, this was in the last lecture as well. And it shows the basic concept of Q switching. Okay. And basic concept mean like how it works. So if you remember, like here, this is your switch in the cavity. Okay. And this one also. One side, left one is closed and right one is open. So when it is open, the light is passing through and the lasers and the photons, they are oscillating in the cavity. And in case of if the switch is closed, there is no light oscillation, but there is a pump, there is a population inversion, All the other processes are going on. Only the cavity is blocked. Okay. So when this cavity is blocked, there is no laser output. When then this cavity is unblocked, then we can see the giant pulse at the output of the cavity. So this was the basic concept in Q switching, and these were the graphically. I mean, it was mentioned in my last lecture. When there is no laser, there is a loss, high loss. When you start the pumping, then gain is developing. Okay, and it overcome the loss here. This one here, it overcome the losses. So losses are going down and the gain is here now. It's steady for a while. And this gain actually, it causes the huge pulse at the output when the switch is released, when the Q switch is opened. So the light passes through and we get this huge pulse. Okay, this was in the last lecture as well. And today's lecture, methods of Q switching. Okay, so methods of Q switching, there are two kind of methods, you can say. Okay, actually there are three kind of you can categorize in three. First one, if you see here, that mechanical method. So mechanical method means that some kind of mechanical devices are used. So mechanical devices can be like a shutter, can be a chopper wheel, can be a spinning mirror or the prism. Okay, so shutter is like this. I mean, you can see here, if it is visualized correctly, you can see there is one hole and this disc is rotating. So when the hole comes in front of the gain medium, we can see the giant pulse at the output of the cavity. So when this hole is not in front of the gain medium, even though the laser is building up, because there is a pump as well and population inversion is going on, but because the oscillation is blocked, so when it is open, you get high output at the end. The second figure here, it shows the chopper. Chopper means there are small holes on this disc, you can see. And whenever this hole come in front of the gain medium, then we can see that the laser passes through. Okay, the same procedure, it's built up, but when the hole comes, then it generates the giant pulse. And the third one here in the mechanical category, two possibility to whether have rotating mirror type arrangement, like mirror is rotating, is attached with a kind of servo motor or something like this, and it rotates in a shorter interval of time. So when the mirror is in front of the other mirror, then the oscillation will start. But when it rotates, the oscillation will stop. The laser will build up, but there is no output. Okay. So these are the, which I explained here a bit, these are the mechanical devices. Okay, it's mechanical type Q switches. But these were like, in these days, these devices are not very much common because it has a limitation. Mechanical things are always have a limitation, like it may not be so fast, okay? And it's slow, it may malfunction sometime. So the more common techniques, these are optical switches. Optical switches mean these are devices like acoustic optic device, okay, and here, and then you have electro-optic device. So electro-optic device is like, we'll see Pockle cell and the Kerr cell, okay? And here, the last category is saturable absorber. So these devices are placed inside the cavity, okay? So inside the cavity means if you have a mechanical thing like this, it has to be inside the cavity like here. If you have a chopper, it has to be inside the cavity like here. If you have any mechanical mirror, that is obviously inside the cavity or one end of the cavity. And acousto-optic and electro-optic devices and saturable absorber devices will also be in the cavity, okay? So we'll see how it works. Maybe this figure is not very much clear here. So it just shows that this is a acousto-optic device or something like this, and these are the voltage which are operating this acousto-optic device. Okay, so here we categorize in active Q switching. Active Q switching, mechanical switching and optical switching is active, okay? Other kind of Q switching, we call it passive, okay? So, but this one, we are starting here with the active Q switching. So active Q switching starting with the mechanical Q switches, and mechanical Q switches, in the last slide, I showed you some of the mechanical type Q switches there. Rotating mirror type, rotating prism type, rotating shutter type, and chopper wheel type, okay? So basically, as I mentioned, that the advantage, this it doesn't have advantage actually. It has mostly disadvantage. At the beginning of the laser, when the technology was not that much advanced, so they were using mechanical devices to generate pulses, okay? And that is definitely is very slow, millisecond or something like this. Yeah, some of the mechanical switches, I mean, they could generate probably nanosecond or microsecond, something like this. And it has different techniques, which I mentioned in the last, and it will come more in the next slide, okay? And the important point here in the down, actually, what you see here is limited by the motor rotation speed, okay? So this technique, it can generate the longer pulses, okay? And like here, it's effective up to, you can see here, this is 0.2 microsecond, a millisecond, sorry, not even microsecond, milliseconds. So it's very much limited to this speed of this switching, okay? Mechanical switch, how it works actually, mechanical switch. So let me see how many people are here now. So Salman is here then? No, I don't think so. Anyway, so mechanical type Q switch, what exactly happened? The mirror on the one side, if you see here, this is the normal, okay? And if this mirror, if we take it out from the path of the beam, or if we remove this mirror or rotate it like this, like in this direction, okay? So cavity is misaligned in this case. So if the cavity is misaligned, so these oscillations will not work as well, okay? So there is no laser output, but pump is not stopped. So population inversion is there, stimulated emission is there, okay? Only just block the cavity. So when this mirror will be realigned again, so we will have this situation. So in this situation, you will get output giant pulse, okay? And that will be, it depends how quickly this mirror can rotate. So how it rotates and how quickly come into the path of the beam and go out. So in this way, it can generate the giant pulses. So probably millisecond or less than that. This is the basic principle, okay? So this is a chopper wheel type. So chopper wheel type, you can see a simple kind of animation, which is very slow. In actually, it's not like this. You can see that hole. That hole actually from where the light passes through when it comes in front of the gain medium. Okay, so when this hole is not in front of the gain medium, it means there is no laser output, but there is a lasing in the gain medium action. Okay, so and it happens once in a rotation. Okay, here it shows twice actually. This is roughly built kind of thing, but it happens once in a rotation. Okay, so this is how a simple chopper, I don't know if chopper is like it's a disc and it has holes on the edges. Okay, and this disc actually it rotates with a certain speed, rotation per second or whatever, rotation per microsecond or whatever it is. Okay, so this is this one. This is a disc and this it has holes, and from these holes a laser can pass through and it rotate with a certain rotational speed. Okay, and then you can have like whatever, I mean maybe it's 1 microsecond per rotation, 2 microsecond, whatever, it depends on the motor. Okay, and when it comes in front of the gain medium, then we can see the output at the output of the laser from the cavity. In the normal case, there is no output because that is blocked, and when the hole come in front of the gain medium, then you get output. Other one which we have observed in the first, actually this one here, the rotating mirror type. But what exactly it look like arrangement, you can see in this slide. Here the mirror is mounted here, okay, cavity mirror, and it's connected to certain kind of motor. Okay, so it's rapidly rotating. So it's not like you have seen that servo motor and stepper motors. So it's doing like this. I mean, like it go through the in the normal direction and then come back like this, like this, like this, like this. Okay. So it depends, I mean, how fast it can move. So in this direction, you can see the laser action, but if it return, then you cannot see the laser action. Okay. So it's a similar procedure like in case of chopper in a different way. And here, other possibility to use the prism. Okay, so prism can deflect the light. Okay, so it's connected to the motor, and from the prism the light can make a retrue reflection and come back here. So if the prism is in the path of the beam, then we have a laser. If the prism is not in the path of the beam, then we don't have a laser at the output. So these are mechanical coincidences. Okay, rotating prism, rotating mirror, chopper type, and aperture type. Okay, and old technique, it's not very fruitful in these days. In any case, we don't need a millisecond. If we need a millisecond, like chopper, wherever you see the laser labs, I mean, they have the choppers. So any CW laser can be converted to the pulse, but very, very long pulse by using the chopper. Okay, so now if we move further, The most latest and the most effective technique is a modulator. So modulator actually is optical switch. And there are two kinds of optical switch, acoustic and electro-optic. Okay. Acoustic means there is some kind of the sound waves are involved. Okay. So how it is we will see. And other one is electro-optic. So electro-optic, there is electric field is involved. Acoustic waves are involved, and electro-optics, electric field is involved. So the method is same. Like one side is blocked. When the switch is on, energized. Okay, energized mean it will not let the main beam to pass through the switch, like here. Okay, so if it is not energized, then it means it's open and the light may pass through. Now, okay, these are the basic things in the Q switching, but you people need to know a little bit what these acousto and electro-optic devices are. The reason is that for the mode locking, when you study the ultrafast laser, sometimes we need to use these devices. And these devices are important because it helps to generate a mode locked laser, where we need it for the ultrafast laser. As I gave you the example that mode locking or gray switching, what is the difference between them in the last lecture. So what is the difference? Who's gonna tell me what is the difference between the mode locking and Q switching? Ihtisham.
Sir, I don't remember clearly, but uh, I, we use Etalon for mode locking, in which we use
No, I think you
electric
don't.
mode.
You don't follow my lectures probably. In the last lecture, I
Is there,
mentioned that there are two kind of techniques: Q switching and mode locking to generate the switching. Okay, to generate the pulses of the laser. So etalon is different thing. Etalon is for the longitudinal modes. So we are not discussing the longitudinal modes here. Okay. So David, I think you know.
Sir,
Yes, yeah. Yes, it's Shyam.
sir, actually, using Etalon, we were actually locking the two modes.
No,
That's
we
why
are
I
not
thought
locking.
it may be.
We are not locking. We are removing the extra modes. Locking is empty. Locking is that you have to keep all the modes. Do not block a single modes and then lock all by some certain technique. Okay, keep remember. So David, do you remember what is the difference between the Q switching and mode locking?
Yes, mode locking is when you synchronize the phase, and when the phase are correlated, they generate a giga pulse. Q switching is when you don't modify the cavity, and they only block the output of the laser at certain time, and then you generate a giga pulse of the laser.
Actually, simple, in the simple words, I mean, you went to some other kind of details. Anyway, let me ask to the next. Fatma Noor Bajwa. Fatma. Okay, Mauricio. Fatma,
yes.
Yes, you can. Mauricio, yes.
Oh, okay. Well, in simple words, I think that light is accumulated in in Q switching, and then the aperture opens and light pass through with a high energy.
Yes.
And the mode blocking is For example, numerous waves add together coherently and in short pulses.
Yes. Yeah. Okay, you are right. So, Rusa. Rusa, are you there? Walaikum salam. So, what do you learn? What is that? In simple words, tell me what is the difference between the queue switching and mode locking? Like, for what purpose queue switching is used, and for what purpose mode locking is used? Rusa, can you hear me? Okay, so let me move to the next one now. Amna Said.
Sir, I think that mod logging can create more short pulses as compared to the queue switching.
Yes. So basically, queue switching is not used for the shorter pulse to generate the shorter pulses. Queue switching is basically used to generate the giant pulses. Okay. And mode locking is for the shorter pulses. Okay. So keep remember. Okay. So what devices are used to have a queue switch, but not the mechanical one? It's electro-optic one, acousto-optic one, or optical switch, you can say. What do you see here on this slide? It's acousto-optic device, or acoustic optic actually. Modulator. Why we call the modulator? It modulates, like the modulation in the radio. When you study the electronics, the amplitude modulation or the frequency modulation. This is here we are modulating the optical signals. So what exactly it happens here? It explained in steps. You know that the acoustic waves, in simple words, I call it sound waves. Okay. And sound waves are generated, okay, in a certain kind of crystal. You can also go through here. It's quartz crystal is used, okay. And this quartz crystal is connected to the piezoelectric transducer. This piezoelectric transducer generate the acoustic waves, okay, sound waves. Second point, RF signal generate the acoustic waves in the crystal. Okay, what is this RF signal? This RF signal, piezoelectric transducer is there. Okay, and this piezoelectric transducer is connected with some devices, and that device generate radio frequency. Radio frequency. What is the range of the radio frequency? Who knows here? Radio frequency. What is the range of the radio? Yes.
It's like, for example, AM is like 1000 kilohertz,
Yeah.
and from
And FM?
AM, that is from 80 to 150 megahertz, like,
Yes.
for example, for FM.
Yeah, FM. So, you don't go to the gigahertz, okay? In the radio frequency, it's a megahertz usually. So, megahertz range frequencies are generated here, okay? And this frequency is connected to the piezoelectric transducers, okay, through some devices. Now, what exactly happened when this RF is connected to the piezoelectric transducer, okay? And piezoelectric transducer, it produces certain kind of waves, okay, which are acoustic waves. So these waves here if you see, like here, because of these waves in the quartz crystal, these waves when pass through in the quartz crystal, so quartz crystal actually, it behaves like a diffraction grating. Okay, you can see in the figure below. Here, okay, this is your piezoelectric crystal or transducer, you can say, and the RF signal is connected to this one. Okay, so this transducer is vibrating with the same frequency, whatever frequency we are getting from this RF source. Okay, and this is your quartz crystal, and in this quartz crystal some kind of waves are generated, and this quartz crystal behave like a grating because of these waves. Okay, so when the light is passing through here, if this is on, the light will not pass through all the way straight. It will be diffracted in some other directions. So the cavity will be blocked. So the cavity will be blocked in this case. If it is on, it will not let the light to pass through straight away. It will be diffracted because of that quartz crystal, which is connected to the piezoelectric transducer. Okay. So if it is off, then this quartz crystal is like a transparent material for the light, and light can easily pass through. Okay, this is the simplest way to explain what is acousto-optic device. But if you see, I mean, physically, if you see, it's quite big. It has a controller which is quite big actually. And this device is not only used in the bulk laser, what we are studying here, is also used in the fiber optics and in fiber optic communication as well. Okay, so on the right side there is a it's not 100% correct, I mean, like it has to be, but it shows somehow, it gives the idea when the incident light it passed through and there is the acoustic waves, then it will be diffracted because of that waves. But if there is no, then the light will pass through like a normal cavity. Okay, okay, now when we are saying about the diffraction, then it means we have to look at what kind of diffraction it is. So if you go here, the last point which is mentioned here, Bragg reflection. Okay, so Bragg reflection, Bragg was a scientist actually, if you must have remembered, study the X-rays or this kind of things at certain angles. So lights are diffracted at certain angle. Okay, it's called Bragg reflection. So light will not take the normal path like it's supposed to be. So there will not be oscillation in the cavity. Okay, I hope you understand in simple way. So this is some more points which is necessary to know the RF signal. Okay, so it has to be like around 100 megahertz range frequency. Okay, and 1 watt power, approximate idea. Usually it's a big box with the this switch is very small switch, but the driver, it's a big driver usually it has. This driver is to generate the RF signal. So this is how it works. It generates the waves in the quartz crystal, and then quartz crystal become like a grating, and it's diffract the light in other directions. So the lights are not passing through straight away. Okay, but the main thing in this one, as compared to the mechanical switch, it's very rapid. Okay, rapid means that it's this, you can imagine that it's 100 megahertz, so it will be very rapid. Another thing actually mentioned here, if you go through here, there are two possibilities actually. One possibility, we can also change the frequency. But in the usual case, when we use this switch for the Q switching, what usually we do, we keep the frequency constant. That is 100 megahertz. Let's assume. And the power of the driver is changed by some way, by some electronic circuit. Okay, so the power is changed and the frequency is kept constant here. Okay, driver power is changed and the frequency is fixed. This will also help to on and off the switch. Okay, and so when there is a power, it means the light will diffract. When there is no power, then it means that the light will pass through the quartz crystal straight away. Okay. Also, this kind of devices, I mean, if we are using very high power laser, and this device is installed in the cavity, and the cavity is generating very high power laser, so we may need some cooling to cool down this crystal, this quartz crystal from where the light passes through. And but anyway, this is an extra thing actually. Usually we don't need water cooling. Okay, but it's very high power, then we need water cooling. But the main purpose here, you people to understand how this switch it works. Okay. Now this is the formula actually, which you can see now on the right side here. This is lambda, capital lambda. This is the velocity, acoustic velocity. This is the frequency. Okay. So you can see here wavelength inside the crystal, inside the quartz crystal. Okay. And wavelength, frequency in the crystal. And we have here the V acoustic, the speed of sound, okay, which is constant actually in the crystal. But in the crystal may be different. In the air, actually, it is different. Okay. So with the help of this formula, we can calculate any of the things which we don't know. Okay. And whether it can be frequency, whether it can be wavelength, whether it can be acoustic speed is usually considered constant actually. Now, if you see, it's more clear how it works here. The RF signal is connected and you have a piezo transducer here. So some kind of sound waves are generated like this. And it causes some, here you can see, it acts like a grating. Okay. So if it acts like a grating, it means when the light will come here and enter, it will never pass through straight away. It will go in this direction, this and this. Okay, Bragg reflection. So if it is on, the light will not pass through all the way. So the cavity will not be functional. Okay. So when it is off, then the light will pass through and the cavity will be functional. Okay. And also it depends. I mean, if the light is coming in like here or light is coming straight away, it depends. Okay. There are, these things are mentioned here. Practically, I mean, how this like grating like pattern is generated inside of the quartz crystal is because of the rarefaction and compression. Lower refractive index, higher refractive index, lower refractive index, higher refractive index, lower refractive index, higher refractive index. Okay. So that is why this pattern is It's like a grating. It acts like a grating. Okay, so who is controlling actually? I feel like somebody is controlling my... David, are you doing something?
Not? No, I'm not doing that.
Somebody try. I mean, I don't know who is using. Anyway. Okay, so here you can read the layers of varying refractive index cause the light diffraction and beam deflection. Okay, and varying refractive index. Keep this thing in the mind. So here, this thing is mentioned here. Compression and refraction. Okay. So refractive, because of these waves, the sound waves, which are passing through the quartz crystal, in the quartz crystal, the refractive index is changing like periodically changing, high, low, high, low, high, low. And because of this high, low, is obvious the light will not pass through straight away. It acts like a grating. Okay. And the second point here, there are two possibilities. It is clear that this quartz crystal will behave like a diffraction grating when the transducer is working. Okay. If the transducer is not working, it's a transparent material. When the transducer is working, so it acts like a diffraction, this crystal, quartz crystal. Then there are two kinds of diffraction may occur. Like you can see here, this is Bragg or Ramannath. So it depends on the orientation of the quartz crystal and your beam. Okay. If your beam is coming like here, straight, then the situation will be different. It will not follow the Bragg. Bragg is only followed when it coming with a certain angle. If it is coming straight, then it will follow the Ramannath. In the next slide, you will see how it is. So what do you see here? Ramannath diffraction and Bragg diffraction. So this is Ramannath. Incident beam is straight away. It's coming here and it acts like a grating and it's diffraction in all the directions. Okay. It may go some part of it, the straight, but it will be very weak signal. Okay. So mostly it will be diffracted around. If the light, incident light is having an angle, certain angle with the quartz crystal, then it will follow the Bragg diffraction. Okay. So this is, it means this is the straightaway beam which passed through here, and this is the refracted beam here. In any case, in both the cases, none of the beam will pass through straight. Okay. So it depends on the orientation of the quartz crystal and the laser beam. Diffraction will happen Bragg type or Ramannath. Okay. Now, if you move further, equation. Okay. This is, if you have studied the Bragg equations in basic physics or something like this, you could understand it. Okay, so what is this equation here? Here. This is lambda. So it's like a 2 lambda. Okay, sine theta lambda over n. So this is this angle actually Bragg angle. This is a refractive angle. This is a wavelength, smaller wavelength. This is a bigger wavelength. Okay, what is the difference between these two? You can see here. This one, which is mentioned here, it's like wavelength in the air. Okay, and other one is wavelength in the crystal. Okay, so Bragg condition, reflection and constructive interference. Okay, 2 pi phase shift, and whenever the waves are like passing through having constructive interferences, you will see at the output. Okay, and the second point, diffraction beam exit crystal at the same angle as entry. Okay. Okay, something is wrong. Something is wrong, I don't know. I didn't understand why I cannot click the pointer. I don't know. Anyway, so intracavity beam deflected out, no amplification when the modulator is on. When it is on, diffraction happen, no light will come out. When it is off, the light will pass through and in the cavity and you can see the output. Okay. And this is the basic equation. I mean, when you study the diffraction or this kind of things to know. Okay, so if we move further, I hope you understand a bit. Even if 50-60% you understand, if you go through again and rewatch it, then probably you will understand more how it works. This is a acoustic wave in AM, one of the problem. Okay, so how to find out the angle of deflection. Okay, so angle of deflection, some of the parameters are given. AM modulator driven by 28 megahertz, this is RF. Okay, and quartz is used to deflect the beam of helium neon laser. We're using this modulator for the helium neon laser. And the speed of the sound, you know that 3,750 meter per second. Okay. In the quartz, actually, in the air, it will be different. Okay. So in the quartz, the speed of the sound is 3,750 meter per second. And the refractive index of the quartz here is 1.46. So what we are supposed to calculate the angle of deflection caused by the modulator when used in a Bragg regime. So this is the formula, and this is the RF frequency here. Strange thing happening, I don't know. Okay, this is frequency, and this is your speed of sound in the quartz crystal. So what wavelength you get inside the crystal, that is 134 micrometer. Okay, and what we are supposed to find out, the angle of deflection. So we have to use ultimately this formula. Okay, so the helium neon wavelength is this one. Okay, and 2 is a constant, definitely refractive index is 1.46, and this is the wavelength which we calculated here. So sine theta, and you can find out theta is sine inverse whatever, which is 0.093 degree. Okay, you can find out some other parameters also. Okay, but the equation is simple. I mean, this equation you must have seen here as well. Here, okay, and here. So you have a speed of sound in the crystal, you have RF, okay, and this is actually here. It's a bit confusing. You can just say is velocity, acoustic velocity. Okay, so you have this thing here. You can find out lambda, which is the capital lambda. We are saying the wavelength inside the crystal. Okay, and from this wavelength, you can easily find out this angle of deflection. Okay, the wavelength of the helium neon laser which pass through, and the wavelength inside the crystal is this one, and you put the values and you can get this theta deflection angle. Okay, so what you have here, okay, so what you have here now, this is if this Q switch, this kind of Q switch, AOM, acoustic modulator, it's inside the cavity. On the right side, it shows that like how when it is off and on, so what happened, okay, and on the left side it shows that the scheme when the light is there and your acousto-optic modulator is there or deflector, how it works. Similar way, like I have mentioned in the last slide, this is a grating pattern, okay, and the light pass through if there is no grating pattern, and if light will deflect when there is a grating pattern here. And when grating pattern will come, when the we turn on the RF signal and some kind of sound waves are produced. And here you can see this is the gain medium, this is the acousto-optic modulator. When the modulator is off, now its energy is building up and it's become off. When it's off, then it's passed through. When it is on, then energy build up. When it is off, then light pass through. When it is on, the cavity is blocked, it's build up, okay, and accumulate all the photons and something like this. And then when it is off, then the light pass through. On and off. When it is on, no light. When it is off, light. It's opposite to the mechanical switch, okay, what we turn on and off. So when we turn on the acousto-optic modulator, the light will be blocked. And when we turn it off, then the light will pass through. Okay, so this is one of the example. You can see how the light, if you see on the left side here, this is the light is passing through without any diffraction effect. And here the switch is on. When the switch is on, the light is diffracted. Okay, so this is one of the example for the YAG laser tested with the acousto-optic modulator. When this on, you can see like this diffracted patterns here, 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 here. And when there is this AOM is off, then you don't see anything like this. Now, the other kind of switch. So other kind of switch, which is also very important, that is electro-optic switch. So electro-optic, it's as its name shows that some kind of electric field is involved in it. And that electric field is not applied somewhere, but it applied to one kind of crystal. Okay, and the crystal changes behavior, its properties, its characteristics. Okay, you can use any word. So here, an applied electric field changes crystal's optical properties. Optical properties, here we are concerning about the refractive index, because the refractive index is changing. If the refractive index changes, then it means the light will change the path passing through. And this kind of experiment you must have done in the high school. Then when the light passes through a glass slab, it changes path. Okay, and I remember all of you must have done this kind of experiment Anyway, so there are two kinds of effect in electro-optic switch. Okay, you can see here index changes linearly. You apply the electric field, refractive index changes. This effect is called Pockels. Pockels were scientists who actually invented the Pockels cell. Okay. Other possibility that when the electric field apply, then electric field apply, the refractive index is not changes linearly, but quadratic. It means you need to apply very high electric field. And this was introduced by Kerr, the scientist. So this is called Kerr effect. Okay. Linear change and quadratic change. Okay. So quadratic change is very minor. If you apply same electric field to the focal cells and to the Kerr effect, in case of Kerr effect, you don't see much difference. Okay. But in case of focal cell, because it's linear, you see the difference. So high voltage we need for this effect in both the cases, and in case of a Kerr effect we need much more higher. And this device can be easily used for nanosecond. Okay, even go to picoseconds possible switching speed. Now below this red line, the same points actually it's mentioned somehow here, and is proportional to the applied electric field refractive index. This is a Pockels effect. And the Kerr effect, a quadratic or electro-optic effect, it's also called the quadratic or electro-optic effect, and proportional to the square of the electric field. Square of the electric field. So if you have an electric field, okay, and here is your electric field, and here your refractive index. This is a linear relation in case of Pockels. Okay. But in case of Kerr effect, you need to have a light twice. Then you will have a linear here. But you need twice the, not the light, sorry, electric field as compared to this one. Okay. So if you apply half the light here, electric field, this effect will not be a prominent. You will not see this effect. Very effective, this Kerr effect. You need a very high electric field. Below, at the end of this slide, you can see small box. What is written there? That all the materials, they can show the Kerr effect, but need a very, very high electric field. Okay. And in case of Pockels effect, we don't need a very high electric field. Disadvantage, okay. But Kerr effect is also, it has some other advantages, okay. So there is one kind of applications, like people want to study the Kerr effect in different materials. And that different materials can be like any material, you can take it. And if you want to study the Kerr effect in it, and you have some arrangement, you can apply some very high electric field. You can observe how much effect is there, how much change in a refractive index. Okay, so Pockels effect is more promising for this kind of switching because you don't need very high electric field. Okay, basically it's changed the refractive index. Okay, so principle of this electro-optic modulator in one line, we can say that voltage induced birefringence in the crystal. Birefringence mean it has a 2 refractive index. Okay, it may have, or at different polarization, refractive index is changed. Okay, so birefringence in a crystal. So what is birefringence? As I mentioned, that you can see from here, light splits into polarization dependent rays. Okay, so one polarization feels a different refractive index, other polarization feels a different refractive index, like here. Okay, so this is a perpendicular type polarization, this is parallel type. Okay, this is parallel type here. So in both the cases, light is having a different path when it passes through a birefringent crystal. A certain kind of crystal is called birefringent crystal. It's related to the nonlinear physics or nonlinear optics or nonlinear optics, actually, basically nonlinear material. So birefringent crystal is there and the light passes through, but if the light have a different polarization, both the polarization will pass through having a different path because of the different refractive index. Okay, so it's a double refraction as well. It's a double refraction because there are 2 refractive index. Okay, so this one is like, you can see orthogonal polarization exit along different paths. Now, one of the example is given here, calcite. Okay, so calcite basically is a natural crystal that exhibit what it has, birefringence properties. Okay, so birefringence nature, when the light passes through, different polarization passes through having a different paths. Okay, so here it's mentioned in this case of index of refraction 1.66 for light in the perpendicular plane and 1.49 for light in the parallel plane. Okay, so parallel plane is this one and this is the perpendicular plane. So it means it's obvious if they have a different refractive index for different polarization, that means they will pass through having a different path. Okay, so we can utilize this kind of property. So calcite is a natural one, but there are many materials actually which are can be birefringence, I mean artificially, or you can manufacture it somehow, you can say. So electro-optic effect, actually, Pockels effect. We study the Pockels effects first in this slide. So this relation is key to understand, that is change in refractive index. This is a constant of materials and this is the electric field. Okay, so it means you can say it's directly proportional to electric field. Okay, it's a linear, okay, and linear function. And A, actually, this constant, actually it's called electro-optic coefficient, and it depends on the material, what material you people, not you people, I mean the people using this kind of Pockels cell or electro-optic modulator. Okay, and it is considered 0 in non-crystalline substance. If the substance is non-crystalline, it may have some, it may show birefringence, but it's non-crystalline. But if it is 0, then it means there is no electric field. Okay, so it means there should be some value of this electro-optic coefficient, and the material has to be crystalline. So one thing is ruling out, that it should not be a non-crystalline. Okay. So there are some famous crystals which are used. You can see here. Ammonium dihydrogen phosphate, ADP, and potassium dihydrogen phosphate, KDP. So these are manufactured. I mean, they make it by combining some materials. Okay. And third one is lithium niobate, or niobate. So you can see the different polarization. Different refractive index. So like in case of ADP, 1.51, 1.47, 1.51, 1.47, KDP also. And in case of lithium niobate is 2.23 and 2.16. It's a prominent difference actually in case. More difference actually, it's good for, yeah, you can separate both the light polarizations. Okay. So these are the common materials which are used, and it exhibits the birefringence properties, something like this. Now the next slide is about the electro-optic effect also, but it's Kerr effect. Kerr effect is actually, as I mentioned, you need very high voltage for this one to observe, and it can be observed in almost all the materials, but it needs a very high voltage. Different materials have different voltage values, but higher it's necessary condition. Here, change in refractive index, coefficient, and twice the electric field. This coefficient here is equal to lambda k. K is a Kerr constant and lambda is a wavelength. Okay. And A2, we can also call it second order because twice the electric field. They use second order electro-optic coefficient. Okay. And it's equal to lambda k. K is a Kerr coefficient, and it's it depends on the material, particular material. Okay. As I mentioned that all the materials can show this effect, Kerr effect, and this effect is very small in the material, so it's really difficult to observe. You need a very high sophisticated some instruments to observe this effect. And very high electric field, sometime or most of the time. It's not possible for us to generate very high electric field. Okay. And common type material in Kerr effect, it can be like liquid nitrobenzene, one of the example there, which is used as a cell in electro-optic devices. Okay, this material, liquid nitrobenzene. Okay, wavelength and K. K is a coefficient, Kerr coefficient, which is depending on the material, and lambda is a wavelength which is used, and E is electric field, very high electric field. And how it works, this is a simple scheme. You can see here what is here. This is a crystal we call electro-optic cell. There is a crystal or there is a liquid which is nitrobenzene, possible, but here we are saying there is a crystal, and that can be a ADP or KDP. Okay, there is formulas. I mean, you can see the formula of these crystals here. And there are two polarizers. One we call polarizer, other one we call analyzer, because it's 90 degrees from each other. Okay, so light twisted when passed through. Whenever we use the electro-optic cell or electro-optic in electro-optic devices, the crystal is used. We need to use the two polarizers. Okay, polarizer where the light enter, and analyzer from where we take the output. Okay, and electric field is applied on the both sides of the crystal. Okay. So electric field is applied on the both sides of the crystal. So that electric field, these electrodes are connected to the crystal, and electric field is applied. And when the electric field is applied, then it shows behaving something that light maybe change its path. So why do we need the polarizer here? The crystal sits between the cross polarizing filters. Okay, these are cross polarizing, like 90 degrees, two polarizers and 90 degrees from each other. Polarization they should have. High DC voltage is used, not the RF, not the alternative, not the oscillating voltage. Okay, so it is the DC voltage. And change the refractive index, obviously. And the field strength can be calculated by using this formula. Okay, E is equal to V over D. V is the voltage, E is electric field, D is the distance. Separation between the two sides of the crystals. Okay. Thickness, you can say, is thickness. So when the light enters here, if the light is having the same polarization and this one is not changing anything, this crystal, then light will pass through, but here the light will block. It depends. It will let the other polarization to pass through, but this polarization to block. Let's move to the next slide where you can understand more. So what you see here now, there are some points here. This animation also you can see meanwhile while reading. The light is polarized before entering the electro-optic crystal because of the polarizer in the beginning. This. Okay. And second point, analyzer. Output light passes through the second analyzer. It depends on the polarization. Okay. So if there is no field, if there is no field, light pass through, no effect on the light when it passes through the crystal. But this light will not be passing through all the way because of the analyzer. No field, analyzer, this one and this one. It let the different polarization to pass through. Okay. So when there is no light, no field, then the light is passing through, but this light will not enter the system or the cavity because of this analyzer. Okay. So in this case, shutter is closed considered. But when it's on, then it will change the polarization, this crystal, and then it will pass through this one. So when the field is applied, polarization rotates 90 degrees, light passes through. Because this crystal will rotate the polarization. Rotate the polarization means that it's birefringence. It's let that polarization can pass through. It has two refractive index. Now see the animation on the right side. Probably it's difficult to understand, but this can help you. Look at the red switch here. When the voltage is on, the light passes through here. When the voltage off, light is not passing through the analyzer. Because this polarization, which is passing through here, this polarizer is not allowing this one to pass through. When this focal cell becomes active, then it will the polarization will be changed, and then this light will pass through here. Okay, and we can see. This is how this thing happened. This is in the cavity. Obvious, when there is no field, the light is not passing through. Okay, and the cavity is inactive. When there is the electric field is applied, then the cavity become active and we can see the light. So when the shutter is off, then the laser is building up, but we don't have output. But when we turn on the electric field, then we can see the giant output pulse of the laser. Okay, so the same thing is explained here. If you see that, here, rapidly changing the light polarization to block output. Okay, and light stay trapped, storing energy in the cavity. Okay, and when the switch is off, stored energy exits as a strong pulse. Okay, so when the switch is off here, when the voltage is applied is on, actually they let the light to pass through. Off here when there is no voltage, no electric field here in this case. In this case. Okay, so this is graphically, I mean, if you want to see that how it works, that time and gain or intensity, you can say. This is basically this focal cell here is different. It's not using the polarizer. Okay, so but this animation is showing without the polarizer to use. Okay, which is not 100% correct, because whenever we use the electro-optic device, not the acousto-optic, electro-optic device, it's always in between the polarizers. Okay, so this is in general, it shows that because when it's turned on, the voltage is applied, the light, because of the refractive index, it may change like this. Okay, and when it is off, it simply acts like a transparent material, so light pass through. Okay, so this animation is not, I mean, predicting what exactly it's supposed to be. Okay, here you can see in this video, if we can play, this is cell here, how the polarization is changing when it passes through. Here is one more thing, anisotropic crystal. I mean, don't go in detail of anisotropic crystal at the moment. And you can see here, this side actually, where is my pen? Here. Okay, so this is the electrode is connected to the crystal. This is the crystal, and the light pass through and it change the polarization. This input light here. And this is the whole assembly. Okay. So what we studied until now, it's categorized in the active Q switching category. Mechanical type, optical switches. Mechanical type and then optical switches. In optical switches, we have like acousto-optic or electro-optic switch. Okay, and these switches are used to generate a giant pulses by Q switching technique. Okay, and we study a little bit about how do they work. Okay, and not in that much detail, but at least you need to know a little bit how it functions. Okay, another one actually which we call the passive Q switching. Passive Q switching, we don't have any like something which is connected to some electric field or some motors or something like this. We have some kind of dye solvent or dye solution, not the solvent, actually dye solution. And what is called, it is called saturable absorber. Saturable absorber, as its name shows, light passes through and it absorbs the light. When it is fully absorbed, become bleached, then it let the light to pass through. This is the dye solution. Okay, so is a dye in a solvent that changes transmission with the intensity. It blocks high intensity, it let the low intensity, or vice versa. It depends. And it is opaque at low intensity, but turns transparent at high intensity. It opaque if the intensity is low, light is not passing through. But if the light is very intense, then it becomes transparent. Okay, it bleaches. So it is placed inside the cavity like other Q switches. Okay, and it is category of the passive Q switching. It's not active, it's passive type. Okay, there is no electric field or nothing, just a kind of solution, dye solution. Okay, and here early in the pumping, when you start the laser, when the lasing action starts, the intensity is low and the light is absorbed in this case. Okay, and the cavity losses will be very high. There is no output. Okay, but as the intensity increases, the absorber to absorb the light, it bleaches. I mean, it cannot stop the light, it passes through like a bleaching powder, you can say. Okay, so as the intensity rises, the absorber bleaches and the cavity loss drops, and we can have something at the output, giant pulse. So at low intensity, losses are high and the cavity build up, and when the intensity increases, start oscillating and produce a pulse. Okay, the transmission of this one is from 10 to minus 6 to 0.3 within few nanoseconds. It's very rapidly working. In the beginning, it's like opaque, low intensity, but when the intensity is increased, then it let the light to pass through, bleaches. And this is happening in a very, very short interval of time of nanoseconds. Okay. This is kind of thing which is complicated in the sense like you can see here that here this is the saturable absorber or dye absorber, and here is also, it's saturated here fully, so it cannot absorb further, so light passes through. Usually it happens high intensity. Here it acts like opaque somehow, some very leakage at the output you can see, but not too much. Okay, so here the light is blocked and here light passes through. Okay, this bleaches. Here it absorbs the light and here it's not able to absorb the light. There are different kind of saturable absorbers. So more the common one which is used is called SysMes. SysMes actually semiconductor saturable absorber mirrors. You can see here. semiconductor saturable absorber mirrors. So with the mirror, this kind of you can see the arrangement of this saturable absorber is attached with the mirror. Okay, and this is mostly used like this. This is substrate, and this is the substrate here, and these are the layers, reflectors, and here you see the saturable absorber. So light enter here, it may reflect from 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 here. Okay, so it enter like this and it may come out like this. Shorter pulse is longer pulse and shorter pulse, or if it is not pulse, at least to have pulse. Okay, so what is written here? Ideal for passive Q switching, this kind of arrangement, and low personal energy. What it consists actually is suitable saturable absorber layers, which is can be a die or something else, and a reflective mirror stacks, this one, and a substrate, this one. Other materials can be used like PBS, lead sulfide, okay, and enclosed in a glass kind of thing, and gallium arsenide can also be used for a basic Q switching, but this one is a common arrangement, this kind of in the market available. So when it is in the cavity, it's obvious that when it is opaque, it's not 100% opaque actually. It will let a light, very little leakage outside. When the intensity is increased, it let all the light to pass through. Okay, so you can have a shorter pulse actually as compared to the other switches in a Q switching category. And you can see here is reversible. When the light become to low intensity again, it become opaque, and high intensity to high intensity to transparent again. Again, it's a reversible process. So low intensity opaque and high intensity transparent. So this is the characteristic or property of this the solution. So material recovered this time and is ready for the next pulse, and recovery time is very short, it's nanosecond range. Okay, and this is comparatively simple as compared to the other active devices, but it has also some limitations. Okay, so what it shows here in this figure, this is your broader pulse, already pulse laser. Okay, so when it passes through the saturable absorber, lower the intensity, losses are high. The intensity increase, losses decrease because the light start passing through. And what at the output you see, like the pulse becomes shorter. This thing will be eliminated because what is in the category of low intensity, it will be blocked. And the peak is the highest intensity, it will pass through. So this one automatically, this portion is reduced, it becomes more sharper here. Okay, so this is how it works. It can also work to reduce the pulse duration. It can also work to act as a switch, obviously. When it doesn't allow the light to pass through, when it does allow the light to pass through. Okay. End of this Q switching, the technique which is used is called the cavity dumping technique. Okay. Cavity dumping technique. In cavity dumping technique, one thing you have to keep it in mind that we don't use any kind of partially reflecting mirrors on any side of the cavity. Okay, here both are, one is a plane mirror, other one is a curved mirror, both are reflecting. Okay, so light cannot go out from any side. It's done. We have a gain medium here, laser crystal, whatever, and we have a optical switch. Here we are saying that the acousto-optic modulator. How we do, or how it works, when it turn on, the light is diffracted. If you remember its working of air, and this light can be extracted from the cavity by using another mirror to out of the cavity. So the light is not extracted from this side, not from this side. It's extracted by using another mirror in the cavity. Okay, and we get some output. This is called cavity damping technique. For the cavity damping technique, this is also switching, Q switching. And the cavity damping technique, we use the AM or electro-optic modulator just to change the path of the light and then extract it with another mirror in the cavity. Okay, so this technique is also used in Q switching, where you want to have Q switching in the cavity. Okay, and difference is that its cavity is different, no partially polished mirrors. Okay, here you see the, if you previous one was with the acousto-optic modulator, and this one with the electro-optic modulator. In electro-optic modulator, you always use the polarizers. Okay, and both these devices can be used for the cavity damping technique. Okay, but in cavity damping, both the mirrors are fully reflective. We have to introduce another mirror in the cavity to extract the light. Okay, so what you see here, focal cell or the electro-optic device is not energized, it's not on. Okay, so the light is passing through as usual. Okay, this is your focal cell, and this is your polarizing beam splitter here, polarizing beam splitter, this one. It split the light on the basis of the polarization. Okay, when it is energized, it applies the electric field, polarization is changed, and this polarization, when it's changed, it can be extracted by using this. It's reflected from this one. Okay, so this is the cavity damping technique. This is also used in Q switching methods. Okay, different methods. So this is also one of the techniques. And it depends what kind of laser is used. Sometimes we need to employ this the cavity damping technique rather than the normal, with the one side is partially polished or something like that. At the end, if you see here, you can see it's animated actually how it works, the gain medium and the focal cell and the graph here. Okay, so losses and low losses, high losses. When it is block here, it has high losses. Okay, when it is, now it's low losses, the beam pass through. Okay, this is the focal cell, and this is your gain medium. Okay, so these are just like a graph showing that how it build up here and how this focal cell is operating. It's block here, it's building up here. Okay, so when it's unblocked, it's also stop building up and release all the energy, and we get at the output. And this is where we get the pulse. Okay, so this animation is very good for you people to understand how it works. Maybe later on you can also observe, rewatch it. So, and at the end, this one you can also observe a bit slow, but it will also help you to understand. This is your cavity, okay, and you have output mirror and HR highly reflecting mirrors, and you have gain medium, laser medium, which is ND-YAG can be, and then you have a polarizer here, and then you have electro-optic device. Okay, so called focal cell, and pumping is starting now. Okay, so when the pumping is started, it start building up. Okay, but it's blocked. Okay, and now with the passage of time, you will see it's building up, and now okay, it started moving, but it's blocked here. The polarization is different because of that polarizer. Okay, now this you can see here. This is unpolarized light actually. When passed through, it become polarized. Okay, and this polarization after passing through is changed, and it moves to the other side of the cavity. Okay, so next step, because it's supposed to move to and fro. Focal cell here, voltage applied. So so here you can see now its polarization change on returning back, but this polarizer is blocking that one, so there is no radiation. Okay, and after a while, sorry, just a minute. Probably in this way you can see. So here, okay, so there is no radiation because of the polarization. You people can see, isn't it?
No, sir, we cannot see.
You people cannot see. Just a minute. Now you people can see. Yes. David, can you see this one?
Yes, sir, I can see this.
Yeah.
Yes, I can see.
Yeah, actually, so this is how, I mean, when there is no radiation, when the polarization is changed, when the same polarization which can pass through the polarizer, you can see. This animation I will also upload to the YouTube, probably you people can understand more. It's pretty long here, and you may not understand 100% at the moment, but if you rewatch and try to listen this lecture again, probably you can understand how these optical switches are working, and it will help you, because next topic will be the mode locking. Okay, so that is the ultrafast laser, the beginning of the ultrafast lasers. Okay, so then this is these devices to understand is necessary, because you people need means that you will need to understand somehow, because in mode locking we need these kind of devices. Okay, so that's all for today's class, and I hope you people understand somehow. If not, you can ask the question, but in the next lecture probably, because I have a meeting after that. And you can go through and you can ask in the next lecture. I observed that you people usually don't ask the questions. I know that it's not a university class where you are supposed to appear in the exam, but it's good for you to understand these concepts probably. Even if your field is not exactly 100% laser, but this is a technology. I mean, you need to know about this, even if you use this. Okay, so let's finish today's lecture. And if anybody having any short kind of question can ask.
Oh, okay. I have one question. Related to why is an absorber in the acoustic optic modulator? I mean, is for blocking the sound waves that not be noisy, or for what is the purpose?
Which one? Saturable absorber? What you are saying?
Yes, with the piezoelectric, there is an acoustic absorber.
Piezo oscillator, you mean?
Yeah.
Repeat your question again.
Why is this device? I mean, the acoustic absorber. What is the
acoustic? Yes, because at the end, actually, we need the acoustic absorber because to absorb the waves which are passing through here, not to reflect again.
Okay,
the waves
okay,
can
yes,
reflect, so it absorbs. Because if it is reflecting back again, then it will be a haphazard. Okay.
Okay,
so,
thank you.
Yeah.
Thank you, sir.
Yeah.
And then with the modulate with the mathematical equation, you can exactly know when is the time to switch the on or switch off. I mean, for example, in acoustic optic modulator, or it's not possible to predict when is the right moment. Or I mean that they do the equation by trial and error.
Yes, I mean, you don't need to calculate. You can turn on anytime. Once the laser is on, you can turn on and off. No need to calculate any kind of time.
Oh, okay.
If I understand your question, probably, maybe.
Yes, it's not necessary.
Yeah.
Okay.
Yeah, it's not necessary.
But okay, and like a suggestion, maybe you can put in the left side a number for the slide. Is that will be more easy to you and for me to ask the specific slide of the question.
Okay. To put the numbers on the slides.
Yeah, yes.
Okay,
to the left.
Next time I will. Next time I will.
Okay, thank you very much, sir.
You're welcome. So, any other question from my native?
Sir, I have a quick question about
It's supposed to be short.
Yes, sir. Refractive index was directly proportional to the electric field scale. So in Carr's effect. So if we, for example, if we suppose the electric field has a 2 value, then for the change in refractive index will be 4. I mean, in Carr effect, electric field strength. Why electric field strength? More electric field strength is needed as compared to the apocal effect. Mathematically, it looks like that small electric field will give the bigger change in the refractive index.
You are saying about the Kerr effect. Kerr effect is clearly, you can see the equation actually. Change in refractive index is equal to E square. So what exactly do you mean?
So if we put a value of E.
No, don't put anything.
I mean, if we put the value of E.
No. You don't need to substitute here. This equation, we metaphorically are showing that refractive index is changing twice with the electric field. You don't go to that mathematical stuff. Okay, it is showing that electric field. Okay, remove this one. Change in refractive index is directly proportional to the E square. You don't need to substitute any value here. We just here metaphorically we are showing that we need twice the light, twice the electric field as compared to the focal cell.
Okay.
Okay, so Mauricio.
Well,
no question?
In the yes, I have a question.
Yeah.
The Kerr effect. Well, I did the experiment at the university, and I could see that the change in the refractive index or maybe in the change in the polarization of light, and it have to it is sensitive with the temperature of the cell.
Temperature also.
Yes. Okay. But in the cavity, for example, in the case of a gas medium, it have a very high temperature, so it affects the cell, or well it affects the change of the. Okay. I think that if high temperature or maybe the cells in ultrafast laser is take or sorry, I cannot I can't
okay. Yeah, okay. I mean, in the next lecture you can I mean, whatever questions you have, you can
yes
interpret in much better way. Okay.
Yes.
Yeah, it seems that you have you know all these things maybe in some cases more than me, because I haven't worked with the Kerr effect because I'm studying here. I mean, I'm showing here actually for you people that this fact is important in the electro-optic devices. So probably we can discuss more. I mean, in the next lecture you can ask your question. Yes, Mauricio. So thank you very much.
Okay, thank you. Thank you.
You're welcome. So, I mean, I hope to have all the students in the next class, because if they are not dropped. Tahura Hadi, you are there? Where is Salman? Tahura. Can you hear me?
Assalamualaikum, sir.
Walaikum salam. Where is Salman, by the way?
Sir, I don't know.
Okay. Okay. Your voice is not clear, probably internet problem. I cannot hear you properly.
Yes, sir.
No, I cannot hear you. I think it's a net problem. So probably if you have any question, we can ask in the next class. Okay. Amna Saida, maybe, I mean, you can also try to ask the question. if you have any.
Yes, sir. Sir, I have a short question. There was
Tahura,
something about.
just a minute. Tahura, I think better to close the mic because we cannot hear you properly. Okay, so Amna Said, quickly.
Sir, I have a short question. Sir, is aperture a slit type thing? And also there was something about cooling and large aperture systems. So this means that the size of aperture also affects the power. Is it so?
The power of the laser?
Yes, sir.
Definitely, I mean, aperture. If the opening is very small, so it will be a less output of the laser, so it will definitely affect.
And sir, is it a slit type thing?
No,
this aperture?
No, this aperture is a round. Slit we cannot use here because we need a Gaussian type shape of the laser. So it's a ring type.
Okay, sir.
Okay. Thank you very much. Thanks a lot, all of you. And keep taking this course. I hope you people join in the next class as well. Okay, David, and thank you very much, all of you. Goodbye.
Thank you. Bye.
Not here. I have more now. What do you want? Okay. Yes, cool.